if you try to call this twice, because you call twice, it's 2t divided by 2 plus theta 1, then your algorithm, the kind complexity becomes linear, right? According to Maxwell theorem. Because A is 1, B is 1. So log of BA is 1, right? So n to the power of log BA is n, okay? I mean, which is like, has a constant higher order than this part, than this part. So the result is the Maxwell theorem where, remember we have, where is, here, 3 cases. Okay, it's going to be this one. So it's like the type, the first one. Because, I mean, it's going to be n to the power of 1 minus 1. Okay, I mean, which will be your, theta 1. So the result is the complexity is going to be case 1. So it's going to be linear. But it's going to be as bad as like a naive algorithm. So you are not getting any, benefit from the divide and conquer, so which is bad. So the next example, it's a Fibonacci number. Okay. So you guys have learned Fibonacci numbers, right? Again, you should have learned that from discrete math, okay? If not earlier, okay? I mean, some of you may have learned that from high school, okay? But anyway, okay, the Fibonacci numbers, the definition is, Fn, equal to 1 if n is 1, 2 if n is, if n is 0, sorry, if n is 0, Fn is 1. If n is 1, Fn is 2. If n is greater or equal to 2, I mean, Fn will be Fn minus 1 plus Fn minus 2. Okay, so this is like a general definition of Fibonacci number. Okay, so using this recursive formula, we can list the Fibonacci number. It's going to be 0, 1, and this one will be, the sum of the previous two terms. And this will be the sum of the previous two terms. 1 plus 1 is 2. This number 3 is going to be 1 plus 2. This number 5 is going to be previous two number. Sum of two previous two number, and so on. Okay? So this is like, you have seen these Fibonacci numbers all the time, right? So if I want you to write an algorithm, okay, want to write a program, okay, for Fibonacci numbers, okay, which take one argument, n, okay, and return the Fn for me, what do you do? Well, the idea, okay, the naive recurrence algorithm. Let's forget about naive recurrence algorithm. Like let's talk about the naive approach. Basically, it's like a loop. Okay, every time you go through a loop, n gets increased by 1. Okay, the base case will be, n equal to 0 or n equal to 1. If the argument you get, belongs to any of these two cases, then, you just return, either 0 or 1. Okay, Otherwise, okay, you just run this loop. You know, the number of times, I mean, depends on like the size of n. So every time you go through a loop, the your you know you get like a bigger number of I mean the next term basically, okay, and eventually you will reach f of n and return this value. So this simple loop, you know, I mean, obviously, like each time you run this loop, it's just a simple addition, okay, and then make sure you place this the previous two terms in the right place, okay. Basically, all the test takes a constant time, and this loop will run pretty much, will probably n minus one times, but anyway, it's it's linear to the argument that you receive. Okay, so basically the naive approach is linear. Okay, and if you use recursive algorithm, okay, this recursive algorithm, how do we use the recursive algorithm to solve this? Okay. It's if you have learned the what's that, generating function and those things in the discrete math, okay, I mean basically you use those ways to solve this recurrence relation. I mean, because actually, here we talk about solving recurrence relation by, I mean, these three ways. But in the discrete math, I mean, you should also have learned how to use how to solve recurrence relation, right? So, I mean, one of them, if basically this thing will eventually be converted into something like eventually you will get like your Fn, try to solve this one, you get like your, I forgot this characteristic equation or something like that. You try to solve this one, which will give you, two loops, right? But one loop will be impossible because it's going to be lower than one. But the other loop will be exactly this one. And then it's going to be like the theta to the power n. I mean, you can use this one to represent your f of n. Supposedly, okay, if you remember something from your discrete math, okay, if you forget, I'm sorry, I may not have time to go through all the stuff. Okay, basically, it's just this one, okay, this formula. You try to use 2 to the power of 2 to the power of x to replace that, and then eventually you get you are able to solve this x. I mean this will give you that formula, and the x will come out, okay, to be something like this one, and then you are able to solve this this one. But then basically you are solving this you are trying to deal with theta to the power of n, right? This first, let me explain. This theta to the power of n is an approximation. It's an approximation. Although it's a close approximation, but it's an approximation after all, because it is not natural number, right? Obviously, it's not a natural number. But I mean, basically, if you look at these Fibonacci numbers, every one of them obviously is a natural number, right? But this one, okay, I mean, just look at this one. It's impossible to be a natural number, right? So this one is an approximation for Fibonacci numbers when n is large. Okay, so first I want you to understand that. Second, once you understand, okay, Fn equal to this one, then you know like how to solve this, right? We just talk about how to solve, the a to the power of n, right? We just talk about how to solve a to the power of n. So if you try to use the same logic here to deal with this, to solve this, then how should I say? You can use a quick way to get the theta to the power of n. Okay, but still, okay, even though we say, oh, this is golden ratio, okay, this is just an approximation. Okay, this is just an approximation. Is there a better way to compute your Fibonacci numbers? So that's our question. Okay, so let's take 10 minutes break. When we come back, we will continue the discussion of this one.